Okay, so a couple quick announcements before we start. I'm going to send out an email today to try to set a time for the discussion section. And on a related note, if you haven't filled out the course survey, please do so sometime soon. As of last night, only a couple people had. I mean, it's not essential, but particularly if you plan to attend the discussion section regularly, it would be good to indicate that on the survey, or just shoot me an email, because we may not be able to find a time that works for everybody. And if we can't, we'll try to prioritize the people who say they want to attend on a regular basis. So, yeah, that's really the only announcement. So today we're going to discuss observational studies. Friday we discussed controlled experiments, which are kind of the gold standard for experimental design. But as I said, in many cases, controlled experiments are impossible. You can't do a randomized controlled experiment of heart transplants, for instance, as that Onion article pointed out. So today we're going to discuss observational data and what to do if you're forced to rely on observational data to minimize the probability of confounding and other bad things happening. So recall from Friday that in an experiment, the researcher is intervening or manipulating the experimental conditions, so that typically you have a treatment group that's receiving some sort of treatment or has some sort of disease or whatever the case may be, in a control group that's quote-unquote normal. An observational study is when you just observe some existing data sets. Experiments are more reliable, but as I said, you can do observational study if an experiment would be too costly or unethical. Study on open heart surgery, or to see if smoking causes lung cancer or anything like that. The reasons why observational studies are generally considered inferior to controlled experiment, well, there's several. For starters, it's a non-random sample from the population. As you'll recall from Friday, anytime you have a non-random sample, you open the risk of confounding. That we saw on Friday in the Salk vaccine trial, that if you just looked at the set of children whose parents didn't give consent to the vaccine, this group tend to have lower rates of polio than parents whose children did give consent. So you do any type of selection in the population, there's a good chance it's no longer representative of the population as a whole. Even bigger problem is that you can't control for any confounding variables. To take the smoking example, if you want to see if smoking causes lung cancer, well, quite consistently, smokers tend to be more likely to drink alcohol, they tend to have lower socioeconomic status, and a number of issues like that. And as a result, it becomes virtually impossible to say it's the smoking that causes the cancer as opposed to one of these other confounding variables. And unfortunately, there's no magic solution to deal with these two problems in every situation. You just have to handle this on a case-by-case basis and and just try to come up with some good solution to minimize the effects of these problems. To illustrate some classic examples in the history of science on where observational studies can get you in trouble, in the 19th century there was this movement to scientifically prove that white people were smarter than everybody else, the other races were genetically inferior, or something like that. So basically what Morton did is he collected hundreds of skulls and measured their cranial capacities in cubic inches, and was trying to compare the brain sizes of Caucasians and Native Americans, and he found that Caucasians had slightly larger cranial capacities on average. Well, as you can imagine, there's several problems with this methodology. The first major problem is that we now know that cranial capacity has nothing to do with intelligence in the first place, but putting that whole issue aside, Morton didn't randomly sample from the population of all Native Americans. He just used a convenient sample of the bones that he could get his hand on. And as it turns out, about a quarter of the skulls he had were from some small-boned Inca tribes, and he had very few skulls from tribes with larger bones. And as it turns out, some close to 100 years later, Stephen Jay Gould reanalyzed this data, adjusting for the non-random samplings to sort of upweighting the larger bone tribe and downweighting the tribes that were overrepresented, and the difference completely vanished. So, aside from the junk science aspect of it in the first place, the point is, if you have a non-random sample from the population, then you'll get a mean that's not representative of the overall population. And a similar example of a more modern case is back when ultrasound was first developed. There was worries about the safety of ultrasound procedures on unborn babies, and which illustrates another case where uncontrolled confounding variables can mess things up. As I said, when they first developed ultrasound, people were worried that it would hurt babies, and so they did some observational studies, compared babies who had received ultrasound to babies who hadn't received ultrasound, and they found that babies who had been exposed to ultrasound had lower birth weights. You can imagine there was a big freak out about this, that nobody wants to have problems with their baby because that had an ultrasound. Well, problem once again wasn't the ultrasound, it was non-random sampling. It was, at this point in time, doctors were less likely to use ultrasound in the first place unless there was some sort of problem with the pregnancy. So basically you were comparing a population of mostly healthy normal babies who didn't get ultrasound to a population of babies who showed some sort of problems who were getting the ultrasound, so obviously you saw a difference between the two groups. Later on they did some randomized study, just randomly assigned some mothers to have ultrasound, others to get some sort of placebo procedure, and found that it had no effect whatsoever on birth weight. Illustrating once again that observational data can sometimes have confounding variables there that can mess up your results. And as I said before, there is no way to completely solve this non-random selection, uncontrolled confounding variable problem, but there are certain things that you can do to mitigate them, as I'll describe a couple case studies of strategies that can be used over the course of the rest of today's discussion. Recall this slide from last Wednesday's lecture on confounding. Confounding means that there's some third variable that affects both the variable of interest and your outcome variable, making it impossible to know if the variable of interest causes the outcome variable. The example I used on Wednesday was there was an association between shoe size, children's shoe sizes and their scores on tests. Turns out that it's not that kids with bigger feet are smarter, it's that older children tend to have both bigger feet and larger test scores. Classic example of a confounding variable that can cause you to believe that there's an association between two variables when in fact no such association exists. So, a famous example of confounding was a data set on graduate admissions at UC Berkeley in the 1970s that illustrates that sometimes if you can figure out what your confounding variable is, you can adjust for it after the fact. In 1973, you had about 8,400 men, 4,300 women applying to grad school at UC Berkeley. 44% of men were accepted versus 35% of women. On face, that seems clearly discriminatory. But it turns out the situation was a little bit more nuanced than that. So, as I'm sure all of you are aware, in every university that I've ever heard of, graduate admissions are made at the department level, not the university level, and some programs admit a smaller number of people than others. And if women are more likely to apply for the more competitive programs, then that becomes a potential confounding variable. And it turns out that this particular data set from Berkeley, that was exactly what was happening. This table here shows the 6 largest graduate programs at Berkeley. I guess this was part of some lawsuit. They didn't want to name the departments by name, lest they get in trouble later on. You can see for these 6 departments that there was virtually no difference in the admissions rates of any of the departments for men and women. In fact, if there was any difference at all, it was in Department A, where women seemed to be more likely to be admitted. The apparent gender bias reflects the fact that men seem to prefer certain programs and women seem to prefer certain programs, and the programs that men seem to prefer seem to be easier to get into. I mean, Department A, you see, for instance, overall admitted some 60-70% of its applicants, and that department had 825 men applying versus only 100 women. Whereas if you look at like departments C, D, E, and F, all had significantly low. Department B was even more lopsided, 60% admission rate, almost all men. C, D, and F, D, E, and F all had much larger numbers of women applying and much lower admissions rates. Hence, it wasn't so much systematic bias against women as women seemed to favor departments that were harder to get into. And you still cannot conclude that no gender bias exists, but this demonstrates if it exists, it's probably more subtle, that the university has less slots in departments preferred by women, or I mean, there's also a possibility that the female applicants are more qualified in general, and that you would have expected more of them to be admitted. And the fact the same numbers were being admitted is possible evidence of discrimination. I mean, there's actually some evidence that that's exactly what's going on at some universities nowadays. So the point is that drawing conclusions from this observational data is tricky, but if you identify these potential sources of confounding, in this case the difficulty of being admitted to a particular department, you can try to adjust for that. I'll give a few more examples later on today. An extended example here is the association between smoking and the birth weight of babies, that there was a question, if women smoke, or does it cause problems with the pregnancy, or the baby's more likely to have lower birth weights? And I'll give a couple examples here of how you can try to adjust for potential confounding variables and try to conclude that there is a true association between these two variables. There have been plenty of observational studies showing that women who smoke have babies with lower birth weight, but you can't establish that smoking causes lower birth weight babies because there's a bunch of potential confounding variables here. Said women who smoke, just to name two of the most obvious confounders, are also more likely to drink alcohol, more likely to be poor, things like that. All these things which are associated with lower birth weight. The question becomes, given all these confounding variables, how can we try to prove that there really is an association between smoking and birth weight, and it isn't just a result of confounding due to drinking alcohol or socioeconomic status or whatever the case may be. So, yeah, I guess I said most of this already. In fact, there were some really weird confounding variables in this data set that, aside from like drinking more alcohol, coffee, lower socioeconomic status, the study found that women who said that they smoked also reported a younger age of menarche than non-smoking women, which is really bizarre because in almost all cases, the menarche occurred before these women started smoking. So why would there be an association there? I mean, it really beats me. The only thing I can think of is it may have something to do with socioeconomic status or something like that, but it's hard to say. It does raise the question, could this lower birth weight be due to the smoker rather than smoking? So the purpose of this study was to try to find out the answer to that question. One way you can try to deal with the potential effect of confounding variables is to just adjust for the confounder statistically. That a follow-up study on smoking and birth rate and birth weight tried to think of every confounding variable they could possibly think of: age, weight, height, blood type, religion, income, education, etc., and then used some fancy statistical modeling to try to adjust for all the potential confounders. I won't give you all the gory details on that today. Later in this course, we'll discuss how you can do this given the values of some confounding variables, incorporate them into your model to see if variable A is still associated with variable B. And what they found is after adjusting for every single one of these 50 variables, there was still a statistically significant association between smoking and lower birth weight. So that's one way to deal with the issue, but it has certain drawbacks as well. First of all, in order to adjust for all these confounders, you have to measure all these confounders, and that's generally not easy to do. In fact, it may be impossible if you're relying on observational data. If you have money to do a follow-up study to measure some of the confounders, you're in good shape. But if you're just relying on a data set from an existing database or what you had money to measure in your disease samples or whatever the case may be, then there's no way that you can get measurements on these extra confounding variables. And even if you have measurements on these confounding variables, trying to dissociate effects of the variable of interest from these other variables is a really tricky problem. And quite honestly, in my opinion, even in the vast majority of published scientific papers out there, people don't do a very good job of this. I mean, I've published papers myself where I don't think I did a very good job of this. It's very difficult to do, and if you don't do it correctly, you can find spurious associations. And the last problem, which may be the most critical one, is there's no way you can ever be completely certain that you didn't overlook something important. In most studies of human disease, for instance, I mean, if you can explain 10% of the association between risk factors and the disease, you think that you've done extremely well. 90% of the variation you can't explain at all. And which means there's probably tons of things out there that cause diseases or cause whatever thing you're interested in you don't measure. And if you overlook a single confounder, this adjustment will not work. So, given the problems of statistical adjustment, what are some other ways that you can deal with this issue? Well, another possibility is to try to find some alternative dependent variable, an alternative outcome that can give some additional confirmation of the association between the variable of interest and the outcome variable. So, in the case of smoking and low birth weight babies, there was another follow-up study that measured certain various measures related to the functioning of the placenta. They found that smokers had more abnormalities of the placenta and higher cotinine levels that's apparently derived from nicotine in the blood. And that gives us additional confidence that the association between smoking and low birth weight is real. In the abnormalities of the placenta, I mean, again, that raised the question, could that be caused by alcohol or poverty or lack of access to health care or whatever? But it's very difficult to understand how you would get cotinine in the placental blood except as the result of nicotine. And if you notice something like that, you say, okay, that increases our confidence that it's actually smoking that's causing it rather than some sort of confounding variable. And in this particular case, I think that's fairly compelling evidence. I mean, if you see placental abnormalities that are associated with the amount of nicotine in the placental blood, well, that suggests that smoking is doing something. But a big problem with this, I mean, you have to find an alternative outcome variable to use. In many cases, that may not be possible. It's if you're testing the efficacy of open heart surgery, you probably really don't care about very many outcome variables other than whether the patient survives the procedure. And even if these variables do exist, it can be very costly to measure them. If you're studying association between smoking and birth weight, and you have money to do a follow-up study where you look at placental blood, that's fantastic. But in many situations, you won't. And if all you have is data that was already collected, you have to analyze, this isn't going to be an option. And even when you can find this sort of thing, it's not a smoking gun to prove causation. Could there be some other lurking variable that's causing the placental abnormalities? It seems unlikely, but we can't rule it out. And also, I mean, do these placental abnormalities definitely cause low birth weight? I mean, it seems reasonable, but we don't have any hard evidence to support that assertion at this point. Another way that you can try to get around this issue is to do what I will call a controlled observational study, which is you take observational data, but you use some of the tricks from that I described when designing controlled experiments to try to reduce the potential source of confounding in your observational data. So in this particular case of smoking and birth weight, what they did is they found 159 women who smoked during one pregnancy but quit before their next pregnancy. And each one of these women they matched to 159 women who smoked for 2 consecutive pregnancies, and then tried to match them based on as many confounding variables as possible, namely the birth weight of the first baby, the amount of smoking during the first pregnancy, etc., etc. And they found that women who quit smoking had babies with higher birth weight than women who continued smoking, offering additional evidence that this association between smoking and lower birth weight was probably real. And I mean, this is another decent solution. It's just, like I keep saying, the rate limiting step in an awful lot of science is time and money. If you have the time and money to do a follow-up study like this, where you try to do some sort of matched pairs design or something like that to control for confounding variables, it helps a lot, but you need to have the resources to do it, and you may not. And once again, you can't be certain that you've controlled for all your possible confounding variables, and you could potentially introduce additional confounding variables that women who quit smoking may also be more likely to quit drinking, more likely to exercise, more likely to go to their prenatal visits, whatever the case may be, than women who keep smoking. So again, you can't completely rule out the possibility of confounding here. But I mean, this just kind of illustrates the point that when you're dealing with observational data, it's virtually impossible to know that there's definitely no confounding going on. But in the case of smoking birth weight, now there's been 3 different studies suggesting that this association isn't spurious. One study adjusted for these potential confounding variables using statistical modeling. Another looked at placental abnormalities, and others did this matched pairs design on the observational data. All of them found the same thing. When you start to see this much evidence all pointing in the same direction, you say, okay, it's starting to look like this association is real. Later on, I'll describe in a little more detail some even more extensive studies they've done on the association between smoking and lung cancer, and describe why almost no one seriously questions the claim that smoking causes lung cancer nowadays, despite the fact there's never been a rigorous controlled experiment demonstrating that, at least not in humans. Another example of observational data and the various issues that can arise when collecting and analyzing observational data, and some of the things that you can do to adjust for it, was this study called the INCAP study that was studying malnutrition in Guatemala in 1969, that basically they wanted to know what happens when children don't get enough to eat and what can you do about it. And basically, this is another one of those situations where it would be highly unethical to design an experiment where you give some children enough food and others not enough food. So we had to do an observational study comparing one group to another, and designing the study required one to deal with a number of different issues. First of all, before they could do anything else, they needed to figure out a way to quantify malnutrition. And the idea that came to mind, well, malnutrition will probably have negative effects on physical growth. Let's see if we can figure out, so let's just do something similar, measure how do something simple, measure how tall children are. They found that on average, Guatemalan children are 5 inches shorter and 11 pounds lighter than children in the US by age 7. Thought that may be because of malnutrition. So why don't we use that for our outcome variable? It has the advantage that it's extremely easy and cheap to measure. If this particular outcome variable works, that would be fantastic. The downside is it may not be a perfect measure of the level of malnutrition, because there's various confounding variables here. There may be racial differences in weight and height. There's also potential confounding variables: disease, hygiene, access to health care, all sorts of things like that. So they had to do some analysis to reassure themselves that this outcome measure of physical growth actually was a decent proxy for malnutrition. So, I mean, one obvious confounding variable here are racial differences that, I mean, even if you look among, like, those of European descent, you have, like, Danish people, for instance, that are often taller than other Europeans, things like that. The question is, well, or the fact that Guatemalan children shorter than American children due to malnutrition, or just due to the fact that they had shorter ancestors and hence they're shorter on average. Well, they looked at upper class Guatemalan children in cities who were racially indistinguishable from rural children, but they weren't significantly different in terms of height than North American children, so they said, okay, it looks like race does not explain this height difference. It's probably caused by malnutrition or at least poor access to healthcare and disease and things like that. This may not be a perfect outcome measure, but it's probably as good as they had. So, said, all right, if we're going to compare heights of children as a proxy for the effects of malnutrition, how do we do that? The obvious solution would be to, well, let's just compare children who get enough food to children who don't. Well, unfortunately, that approach didn't work for various reasons. The first problem was in that day and age in rural Guatemala, virtually no children got enough to eat, as sad as it is to say it. And that aside, in order to do this type of experiment, you would need a record of which children got enough food and which children didn't. And typically, if children aren't getting enough food to eat, people aren't bothering to sit there and keep records that my child did not get enough food to eat this week. I mean, yeah, there was just no way to know which children got enough food to eat and which ones weren't, and there was also no way to control for confounding variables. Most likely the children who weren't getting enough food to eat were also the ones who didn't have access to health care and all these other potential issues. They decided some level of experimental intervention was necessary. So, from a statistically ideal perspective, what you would want to do is randomly sample a treatment and control group from the population of all Guatemalan children, hold their environments constant, but give one group more food to eat than the other, and then compare the heights of the two groups. Step one is impossible, that there's no way you can randomly sample from the entire country of Guatemala. And step two, aside from the fact that holding their environments constant would be impossible, giving one group not enough food to eat would be highly unethical. So that would be the perfect design from a statistical perspective, but it's not going to happen. They had to figure out some other design that would control for the effects of confounding as best as possible and also not be completely unethical. So the way they did it in the INCAP study is they identified 4 quote-unquote similar villages that had roughly the same population, roughly the same poverty rates, literacy rates, and stuff like that. And they assigned 2 of the villages to be in the treatment group and 2 to be in the control group. And the treatment group got a free drink that was high in calories and protein, and villages in the control group got a drink that was low in calories and didn't have any protein. So they were hoping to do us as close as possible to the randomized controlled experiment where all confounding variables were controlled for, but ethically, when these children weren't getting enough to eat in the first place, they couldn't limit the amount of drink that they gave them. So they just let them drink as much as they want and had to collect the data on that, and not surprisingly, consumption varied quite drastically from one individual to another. Also unsurprisingly, children in the control group tended to drink a lot more than children in the treatment group, given that the drink was lower in calories. Hence, it became something of an observational study rather than experiment. Well, it was an observational study in the first place because you couldn't control for everything, but it became even more observational in that not even the level of the treatment variable was controlled for. So, to analyze the data, they had to account for potential confounding variables. Remember the statistical adjustment idea that I talked about earlier, that some big confounders would be the heights of the parents. If the parents were taller, the children are more likely to be taller just genetically. The parents' socioeconomic status and all of that stuff. So basically they fit a statistical model that adjusted for as many potential confounders they could think of, and then they examined the relationship between the consumption of the supplement and height. And they found that in the control villages, they didn't see any relationship whatsoever between the consumption of the supplemented height. In the treatment village, for each pound of supplementary protein the children consumed, they were about 0.04 inches taller on average. So this indicates that the lower height of Guatemalan children is probably at least partially explained by lack of protein, but we still can't rule out the possibility of other confounding variables. Maybe if your parents are taller, you just have a genetic disposition to want to drink more protein, and they tried to adjust for that. But like I said, that sort of adjustment is tricky. Oh, we cannot be absolutely certain that it was lack of protein that caused this. Oh, by now you're probably wondering, as I'm hopefully making you all into good statisticians where I say over and over again, well, we see an association here and it might be an association between A and B, but we can't be sure, and we just get like cynical about everything. And I remember I had a friend once that was a statistician. We had this discussion like, do you ever doubt the very existence of the world? There's nothing else really out there. And he's just sitting here like, no, not really. I don't think so. Anyway, so this raises the question, well, if you want to do any level of science, statisticians always prefer to err on the side of caution and not say that A causes B and end up being wrong about it. But if the government's giving us millions of dollars to do science, they don't want these fluffy papers saying, like, well, we saw something that might be an association between smoking and lung cancer, but we're not really sure, so we don't know if we should say that people should stop smoking. We don't know for sure yet. People want to be able to say, no, smoking causes lung cancer. So that means, when is it safe to say this? What types of evidence do you need to collect in order to safely conclude that variable A causes variable B? And I said, very rarely is there going to be a smoking gun, but you can do various things to convince yourself there's an association between A and B, and the more such evidence you collect, the more confident you can be. And in the case of smoking, there's almost absolute certainty at this point that back in 1965, when this association between smoking and lung cancer was first observed, there was quite a bit of controversy about, is it smoking that's causing lung cancer, or are there confounding variables here? In fact, R.A. Fisher, who was kind of the father of modern statistics, was kind of notorious for being quite outspoken about the fact that he didn't believe that there was sufficiently convincing evidence that smoking really caused lung cancer. So in a landmark paper back in around 65, an epidemiologist named Bradford Hill proposed a list of 9 criteria that you can use to determine when correlation is likely to imply causation. And as I said, you can never be absolutely certain, but in general, the more of these criteria that are satisfied, the more likely it is that A causes B. So, first criteria that he proposed was strength, that strong correlations are more likely to be causal than weak ones. smokers are something like 15 times more likely to develop lung cancer than non-smokers. And when you're talking about epidemiological risk factors, I mean, that's gigantic. Usually it's something like if you're obese, you're 1.3 times more likely to develop heart disease or something like that. Well, an association that strong is more likely to be a causal association. Another criteria is consistency. Do you see the same correlation in varieties of different circumstances? The association between smoking and lung cancer has been observed among the rich, among the poor, among various racial groups. It's been observed in every culture and study ever conducted, which gives us additional confidence that it's real and not due to some confounding variable in some particular subgroup. And another criteria is specificity, that if a variable, a predictor that's correlated to a single outcome is more likely to be causal than something that's associated with multiple outcomes, that smoking increases the risk of lung cancer, maybe a few other things, but it is quite specific to lung cancer, versus something like obesity is linked to all sorts of things, and it becomes much harder to say that is an association between obesity and cancer due to the fact that being overweight causes cancer, or could it be due to the fact that overweight makes you risk of other diseases, which increases the risk of cancer, or if you're overweight, you're just less likely to take care of your body generally, which increases the risk of cancer. Another criteria is temporality, that does the predictor happen before the response, that do people develop lung cancer only after they smoke? Studies have been conducted showing that is in fact what happens. Another criteria is gradient, which is basically when the predictor increases either in terms of magnitude or duration, does the response also increase? In the case of smoking, they found that the longer people smoke, the more likely they are to develop lung cancer, and also the greater the number of packs per day that are smoked, the more likely they are to develop lung cancer. And another criteria is plausibility, which is somewhat subjective, that but the idea that ingesting something into your lungs could mess up stuff in your lungs does seem to at least pass the smell test. And coherence is the correlation consistent with other known relationships. For example, they found that chewing tobacco is associated with cancer of the mouth and throat, once again suggesting that there's probably something carcinogenic in tobacco. And another criteria is experimental evidence, that if you observe a correlation in an experiment, it's more likely to be causal than correlations observed in observational studies. And with smoking and lung cancer, obviously there's never been a rigorous controlled experiment in humans. They can do this with rats, where they expose some rats to tobacco smoke and don't expose others to tobacco smoke. In that case, the rats that were exposed to tobacco smoke, those that were exposed to tobacco smoke had higher rates of lung cancer. The final criteria is analogy, which are other relationships believed to be causal based on similar types of evidence, and that's a little harder to tie into the smoking example. I mean, the best thing to illustrate there would be that, like, if it's already accepted that smoking causes lung cancer, and you want to see does chewing tobacco cause cancer of the mouth and throat, then one could say that one could run the same types of experiments did with smoking and say, since we accept that smoking causes lung cancer, we probably accept this other causal relationship between chewing tobacco and cancer as well. Oh, the main things to remember for today is that observational studies are problematic and considered inferior to controlled experiment due to non-random selection and uncontrolled extraneous variables. So, anytime you do observational data, you should try to minimize this damage by controlling for the confounding variables as best as you can. The best approach depends on the problem, and it's just something you kind of have to think through carefully and learn from experience. On the homework, there'll be some examples of experiments with potential confounding variables that will ask you to try to deal with the confounding. And even with controlled experiment, you can never prove causation definitively, much less an observational study, but you can do various things to reduce the chances of confounding. So, any questions about anything today? I will try to send out sometime this afternoon a link to a doodle poll to choose the time for the discussion section. I'm hoping to get that finalized sometime in the next few days, and hopefully we'll set times for Erica and I's office hours as well. In the meantime, feel free to email me if you have any questions about anything.